on this recording in progress. So all of our Rhino workshops so far, we've done by me doing something, giving you a file, and then you following along with me in real time. Today is going to work slightly differently. And the reason I've emailed you a file. That file has a few different things in it. So there's a folder that I've emailed you a link to that has a program, a plugin that you can install for Rhino, along with some instructions about how to get it installed, and a Rhino file that goes with that installation. But what I'm not going to do is get everyone to install that plugin right now, because that's something that you can, like, it's really simple. You can do it on your own. The computers here, I'm currently working on getting that plugin installed for all the computers in the studio. So it will just be a thing that will always be there. But for now, you can definitely do it on your home versions of Rhino. And you'll also be able to, it'll even work if you have an evaluation copy of Rhino. So if you've just downloaded a trial version of Rhino from their website, the plugin will work on that, and it's free. And we have a Brooks license for it. So it's a specific to Brooks license key. So everything's above board and it all works, which is good. The plugin is called ClimateStudio, and it's probably not something that you've used before. But those of you who did SAED last year will have used probably, I imagine, very, very similar types of programs. The difference is that ClimateStudio works natively within the Rhino environment. So you can build something in Rhino and instantly test out how it's going to perform in a whole load of different climate environmental metrics, rather than building something, then exporting it somewhere else and then running a whole other program. You can make changes live and see how it affects the performance of your building. Does that make sense? That's the main reason why I have used it. Is this the right one? Yes. Yeah, so that's what I was going to say. The idea is this is recorded, and I will just start screen sharing. So it's screen sharing on the recording. Here we are, and let's just make sure that that's actually working. Top to top, hide floating controls. Screen. Let's just share the whole desktop. So this is recording. The idea is during the week, you can then watch this lecture, pause it, fast forward, rewind, go back, go forward, see what it is that I've been doing, and do the same things to two different models. One is the model that I've included in the Rhino file, but the other is your own Rhino proposal, your own model in Rhino. So the idea is that you've got something that now you can start to make quantitative data analysis of, in terms of how it performs in terms of its daylighting, in terms of its glare, in terms of its solar gain, in terms of its environmental, in thermal performance, all sorts of cool things. And so when you then turn around and say, I know my proposal works because this is one of the tools, and I'm going to stress it's one of the tools. It's not the be all and end all. This is, and we'll see as we go, it's a design tool. So it allows you to make a change, see how it affects things. It's not about saying, it's really important for me to know exactly how many kilowatt hours of electricity or gas or whatever I'm going to use in a year. What it is about is being able to say, when I change this element of the design, this metric goes up and this metric goes down. So how do I choose where to put things? As we play, we'll kind of figure that out as we go. So what I've got here is a Rhino file with a few different things. I'm going to talk a little bit about just the concept of environmental modeling and simulation for those of you who haven't done it before, but many of you have. Then we'll go through site and climate analysis tools. Again, this isn't the all and end all, but these are some tools that get you started in terms of quantitative. So we're talking about numbers and data here, quantitative analysis of your site. Then we're going to look at daylight hitting the inside of the building. So what's it like inside my building, given the design that I have with openings and glazing and all the rest of it. And then we're going to have a look at the thermal qualities of the building and how we might model that. The bottom here is a list of instructions about how to install ClimateStudio on your computer. It's really simple. You close down Rhino, you run the installer. If it's on Windows, it doesn't work on Mac. Sorry about that for everyone who's trying to use Mac, but it does work on Windows. And then you restart Rhino and it works. And then the first time you do anything, it'll ask you for a license key, and the license key is included in the file there. So a cracked version of Windows, I don't know. I'm going to imagine that it may or may not work, and I bear no responsibility for whether it does or doesn't. If you want to talk about cracked software, we can, but I have feelings about it, which are less to do with legality and more to do with the fact that how much is a student version of Rhino? Like £100, £120, something like that.
Free if you get it on apps anyway.
It's free if you use it on. Okay, brilliant. Well, in that case, I just feel like the hassle of dealing with the fact that your software works 90% of the time is more than outweighed by the slight inconvenience of having to pay a bit of money and get a real version of the software with support and updates and the fact that it works all the time. But that's just me. If you get to the end of the year and you're about to do your final render and the whole thing crashes and you lose your model and you curse yourself in the past for not having done it right, then, you know, we'll see. Right. What have we got here? I've got a daylight model, and I've been really, really organized, and I've given you some layers, some sub layers within this daylight model. I've got wall. I've just called it wall because I don't yet know what it's made of, but at some point we're going to start saying what it's made of. I've got a roof. It's this guy here. It's got a hole in it. I've got another layer that's hidden at the moment called roof 2, where the roof kind of overhangs this big glazing on the south side. So we could have a look at how that affects things. So we can switch between different roofs. Got a floor, which is just a surface on the ground. Ooh, there it is. That's the floor. I've got some glazing, which I've colored a kind of blue color, and in Rhino I've given it a little material that's glass, which means that if I switch to my rendered view, then I can see through it, which is kind of helpful just for being able to understand what's going on. This material is just visual, like it doesn't know anything about the glass, it just knows that it's transparent. That's all it is. I've put some mullions in my glazing just to sort of give it a sense of actual reality. I've got this layer of like, maybe, you know what we were talking about in terms of like Lego, like where you've made some catastrophic error in your design and you just Lego brick on something to solve a problem. So, you know, maybe there's like a little bit too much light coming in on the south side. So I've just chucked a brise-soleil on so we can see how that affects things. I've got this version of a roof light, and I've also got a different version of a roof light that's a north light. So this is the glazing of on the north side. I haven't put a material on it, so you don't just see. Let's just do that. And glass material on here as well. Go, and now it's see-through. And you'll notice that this is a really simple model. I'm not like going overboard. I'm not going into huge amounts of detail. And yours is going to be much more exciting than this, because this is literally just a rectangular box for me, but your proposals are going to be much more interesting. But anyway, let's go back to the simple first type of roof light, and a few different kinds of windows. I'm just going to chucked around here. In ClimateStudio, when you install it, you get some buttons along a tab that you can put anywhere. You can dock it anywhere in your viewport, and you also get in this area here, next to properties, layers, and all this kind of stuff. Right at the end, you'll have this little blue C, and it's called CS workflows. Can you see that? The sun's kind of in my face, but hopefully that's coming through. CS workflows. And the way this works is basically this is the panel that you'll spend a lot of time in when you're setting up your simulations. And these are well, the most simple way of doing it is these are going to start with you having to give it some information about where you are in the world. Because if you're building a building in Singapore or Jakarta or I don't know, Agra or New Delhi, I don't know, somewhere that's hot, you're going to have a very different set of requirements on your building, as opposed to if you're building it in Antarctica or Greenland or somewhere really, really cold. So not only that, but obviously in different points on the Earth, you're going to have the sun rising and setting and being at different angles throughout the day. So the physical structure of your building is going to get light in at different angles. And so the first thing on the list of workflows is site analysis. The first step in environmental design is to really understand your site, and to understand it not just in terms of here's a sun path and draw a smiley face on a plan, but where exactly is the sun going to be pointing at different times of the day? How do you even know how to get that information? We've looked a little bit before at Rhino's sun. So with Rhino, you can type in sun and you can turn it on and you can set a location and a date and time. This is a little bit more involved. Let me just turn the sun off for there. This is a little bit more involved. Here's a sun path. The next item down, just after you've chosen your workflow, so we're on the workflow of site analysis, is a little icon that's like a globe and then Boston Logan International, which tells me that currently there's the data that's loaded is for Boston Airport in the United States. This software was made by a collaboration between Harvard and MIT, so it's US centered. So they just kind of chose a random city in the US and said, well, there's my default location. But if you click on that, and then there's a little folder icon here, you can browse through the files that come with ClimateStudio. And you can see these are all the locations in the world for which there is data that ClimateStudio can understand. And this data comes from Energy Plus weather. So if you've done, again, SAD last year, you probably spent a lot of time in Energy Plus or using Energy Plus weather data. Design Build. So Design Build uses, I think, EPW files. Did you come across EPW files before? These are EPW files. And what EPW files are are a specific file format that says, I have recorded, in fact, you can even look.
Just a quick one.
Yeah.
For this program to function fully, do you need like a airtight building? You know, like some programs, if you have collision or something, they get an error.
Collusion. Oh, collision. The daylight stuff, no. The thermal stuff is really sensitive. So the daylighting, you can be a little bit more haphazard with your modeling, but with the thermal stuff, and we'll talk about thermal modeling, but actually what you end up doing with thermal modeling is building a whole new model, but it's really simple. So it doesn't take you very long at all. But for daylighting, yeah, if you've got like two items that like collide with each other or aren't quite like meeting, it's okay, it'll forgive you. It's better if it's modeled well. And with this model, I've made sure that the roof exactly joins the walls and it's all in the same place. But yeah, it will let you off. Any plus weather data. Energy plus. Oh, this is Design Builder. Well, this will tell you because the Energy plus weather, it's an open source file format, and what it effectively does is it gives you climate conditions for a location. And that doesn't mean last year it was 21 degrees C on July the 3rd at 10:30 in the morning. It's on average, you can expect 10:30 a.m. on July the 3rd of every year to have roughly this kind of temperature and roughly this kind of humidity and roughly this kind of climate and this kind of cloud cover and this kind of sun angle. Well, the sun angle is accurate because the sun angle is given by the rotation of the Earth and the sun around the sun. But you can read about exactly how they come up with the data. But basically, what you can say is, this is the climate I should design to. Yeah. Now, our site is in Oxford, and luckily, Oxford University has a weather station. And the weather station captures data for years and years and years. And then Energy Plus Weather does a really nice thing where they kind of average out all of the kind of aggregate data, and they come up with a plan for this is how you should expect your year to go. So it's going to be hot in the summer and cold in the winter, or there'll be a rainy season and a dry season, or there'll be a whatever it might be. And you can, and literally once you've clicked it, it'll download the file if you haven't got it already. And then our site is now Oxford University. And you can read a few things about it. You can say it's temperate, which means it's not like super hot or super cold. It's just kind of like fairly livable. There's no dry season or monsoon, so it's not tropical. And the summers are warm. So it's not like Australia where the winters and summers are kind of reversed. You have, I mean, it's hot most of the year round, but you have a Christmas on the beach, and summer is kind of in your house, sheltering from the rain. The average annual temperature is 16 degrees C. The annual total solar radiation, 1,710 kilowatt hours per meter squared, which is really helpful because that kind of gives you a rough idea of cloud cover. If you're going to use photovoltaic cells to generate electricity, that's a number that you're going to really need in the real world. For this design, maybe you don't need to go down quite that kind of level of data, but it's a good idea to be able to say, oh, this data is all available to you. It's all here. Okay, once we set the site, these values here. Oh, hang on. It says USA, Oxford University AP. Well, that's no good, is it? Well, look at it. The reason I can tell it's wrong is because it says it's 34.38 degrees north and 89.53 degrees west, and that's not the UK. Country USA. In that case, there is no Oxford file, which the closest one is going to be London. And look, there's loads of Londons. GBR is the country and the latitude 51, longitude 0.05. That's where we want it to be. So for now, let's just say, okay, London. London pretty much has the same climate as Oxford, really, like they're down the road from each other. So we should be pretty happy with that. Temperate, no dry season, warm summer, 12 degrees C annual temperature. Okay, so the annual temperature has come down quite a bit. Less total solar radiation. We've got like, what was it, 500 less kilowatt hours per meter squared, bit more overcast, bit more wind, 4 meters per second. So, you know, you can start to use some of this data if you want. Coldest month is February. This is the coldest week, which is between the 12th and the 12/15, 12/21. December is the coldest week. Okay.
Americans with birthdays.
Oh man, these Americans. Oh yeah, you'll see later the thermal calculations are all done in dollars. But it's okay because all you're just doing is comparing things rather than like getting exactly into things. All right, so we've got some data about London in this case. The next tab is a little sun, and within that tab is a whole load of stuff. So the first thing is the sun path, and here we can tick this box, and boom, got a 3D sun path. Oh, that's exciting, isn't it? And if you've modeled your proposal in the center of your Rhino file, like on the XY axis at the center, the sun path will sit like bang over the top of it, which is kind of cool. But if you haven't, you can click set position and like put it over wherever you want it to be. I'm going to set position and put it back in the middle here. In fact, if I go to wireframe, there, I can put it in the center of my Rhino file. So there's the sun path, and it's 3D. So we can kind of get a much better understanding of where the sun is coming from and where it's going to hit than our 2D things. However, you can also take this plot, this sun path plot, and export it to a PDF or a PNG and put it in your portfolio, or you can put it to a PDF and then overlay it in a plan in Photoshop or Illustrator or something like that. So you can have the 2D information, you set how big you want it to be, and then you save the file, or you can put it in your actual viewport and then take a screenshot. Those are all good ways of doing it. And then we can also say, okay, well, the date, what's the date today? It's the 2nd of November. So I'm going to set that date to the 2nd of November, November the 2nd, and the time is 9:39. So it's we're about here, aren't we? And so what that tells me is the sun is coming from this angle, which when I look at the sun, that feels about right, doesn't it? That tells me that if I know the sun is coming from this angle, then north is going to be that way, something like that. Does that feel right? Yes, that does, because that's London Road going up towards the Ring Road and the motorway, and then down to London. Okay, so what we've now got is the ability to tell exactly at any time in the year exactly where the sun is going to be hitting our proposal from in 3D. And we can click shadows, and we can see the shadows on that day. So right now, you can see how far into our proposal the shadows from that south glazing is going to go, exactly where the shadows from this side glazing is going to be. And obviously these are north facing, and then these are west facing, so they're not getting any sun at the moment. But obviously as the day goes on, sun comes round, then they start coming in, and then it goes down. And we can trace a whole day using this slider. A nice set of screenshots for your portfolio that you could put together in a kind of nice like film. Maybe even make an animation of it. That'd be nice, wouldn't it? Okay, so we can play with that. Great. You might say, we've seen all this before. This is basically what Rhino can do already. let's turn the sun path off and show a 3D windrows. Again, on site. So this is where the wind is coming from, and this is how strong it's going to be. Again, you can export that plot for your portfolio, make it look however you want. You could export it as a PDF, take it into Illustrator, change the colors, change the fonts, make it look how you want it to look to match your graphic design style. And you can also filter. So you say, actually, you know what? I don't care what the wind's doing at midnight because my building is only occupied between the hours of 9 and 5. So we can filter the times which we're getting the data from to 9 to 5. And now that's only taking into account wind during the day, the working office day. Or you can just aggregate the whole data across the whole year. Maybe you only care about what the wind is doing in June. Something like that. Well, then that shows you a very different picture of what the wind is doing, because when you look at it across the whole year, those averages those peaks get averaged out. But maybe in June, oh, look at that. There's actually quite a bit of northwest wind that you didn't think was there. So that's a lot of fun to play with, just to be able to kind of understand really visually what's happening on the site, environmentally speaking. Next tab, and we're literally just moving through the tabs. Diurnal averages. Diurnal just means, I think it's day and night. So it's like just every day, what's the temperature like? And what it does is it gives you this lovely graph here, which I think I will just expand out a little bit. Here we go. Oh, by the way, the other cool thing that ClimateStudio does, it gives you a compass in the bottom of every viewport. So there is now no excuse for not having a north arrow on all of your plans. And it's really clear wherever you look, which way is north. Cool. Here we go. What it does is it says an average day in January looks like this. Yeah. So an average day in January starts off cold, 6.6 degrees. And then the sun comes out and it warms up and it gets to like 8, 9 degrees. And then the sun goes away and it gets colder again. So that's the temperature of a normal day, like an average day in January. But an average day in July, look, starts 15 degrees in the sort of early morning before dawn. Sun comes out and our average temperatures go up to like 20, 21, 22, and then the sun goes away again and it goes down. So what we're looking at is, this is a snapshot of a year in terms of temperature. Does that make sense? Does anyone want to ask any questions about that?
Why are there many lines in the orange bit?
The orange bit. So the surface of the Earth is curved, right? You're a sphere. And there are two different ways that the sun is going to hit the surface of this sphere differently depending on whether you're at a pole or whether you're at the equator or somewhere in between. So if you're at the pole, the sun comes in sideways to you, and it hits basically kind of, through the atmosphere effectively. If you're at the equator, the sun pretty much hits you entirely from above your head, like normal to that surface. So what you've got is global horizontal radiance, diffuse horizontal radiance, direct normal radiance as well. Direct normal radiance is like, if you're at the equator, you expect that red line to be really high, but the horizontal line, like there's no light coming from here, is there? Like, because it's just like the sun isn't down here, the sun's over here. So if you're at the equator, you're going to have a really thick a big red line, but your yellow and your brown lines are going to be a bit lower. If you're up more towards the poles, your yellow and brown lines are going to be a bit higher and your red line is going to be less. But it goes even further and it says not just where's the sun coming from, but If you've got lots of cloud cover, that's going to mean that you'll get more diffuse radiance. So the sun is kind of being diffused through all the clouds. So it has information not just about which bit of the which angle of the sun is most at work, but also if there's lots of cloud cover, then that's going to give you an impact on that as well. And then the wet bulb and dry bulb temperatures you can read about, but most of the time when people are reporting like the weather on the news, they talk about the dry bulb temperature. The wet bulb temperature is a little more consistent, but it doesn't make so much sense to most people because it feels lower than it actually is. So again, you can take this chart, you can export the plot, you can say this is the year. What's interesting is if we compare it to somewhere that's tropical, I always think of Jakarta as like a tropical place. And then we look at the diurnal average for Jakarta. Do you see how the year is basically the same all the way through? So, and this chart is the thing that's going to show that more obvious. It's like it's a snapshot of the whole year of the climate in terms of temperature. Okay, let's head back to London. London City. Go. Right. Psychrometric chart. Oh, it's so exciting. Sorry, you probably can't even, can you read that psychrometric chart? It's pretty small. A psychrometric chart has two main aspects to it. One is humidity and the other is temperature. It's one thing to know that it's hot. It's another thing to know that it's hot and dry or hot and humid. Those two things are very different. Who's spent lots of time in a hot and humid climate? Who's spent lots of time in a hot and dry climate? They're different, aren't they? They feel different, they act different. Cooling buildings is a different process in each of those situations. If you live in a climate which is super humid, super saturated with moisture, then what happens is you sweat a lot, right? I've found this. You realize your body is producing all this moisture, but it's not evaporating because the air is already saturated with moisture. There's nowhere for it to go. So using evaporative cooling in your humid climate is going to not be as effective. In the same way as that your body is going to try and sweat, but your sweat's not going to go anywhere. You go to a hot but dry climate, your sweat, it's gone away in an instant. So if you want to use evaporative cooling in your hot and dry climate, it's going to work incredibly well. It's going to take all the energy with it as the moisture evaporates. Your only problem is where are you going to get the moisture from? And so what this does is it puts a blob for every meeting of a certain level of humidity and a certain temperature. And the darker the blob, the more hours of the year have that temperature and that humidity. So again, if we say this is London at the moment, you can see that there's a lot of blue blobs, really dark blue blobs, 442 hours of the year, have a temperature between 8 and 9 degrees, but a humidity between 4 and 6 grams of water per cubic meter. 444 hours have a temperature between 12 and 13. It's down in the slightly on the colder side, less humid kind of end. Again, if we change to, let's say, Singapore. Singapore? Have I typed that wrong? Singapore. Oh, maybe they don't have any data for Singapore. That seems sad. Let's find a tropical location. Anyone? Malaysia. Capital of Malaysia is Brilliant. Downloading that file, set that. Look at that. Kuala Lumpur, lots of hot temperatures, much more humid. that make sense? So it tells you something about how you are going to approach the process of, do I need to heat my building? Do I need to cool my building? How might the best way of heating and cooling that building be? And again, you can set that plot, export the plot, put it in your portfolio, make it look amazing. You're getting the picture, aren't you? Any questions on that, or should we move on? This guy, I wonder if I can, if I do this, I can make this a bit bigger. Here we go. Nope. What? No. 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 Everything's broken. Ah. Yeah, here we go. All right, hourly heat map. This, I think, is going to be fairly self-explanatory. Can anyone hazard a guess as to what we're looking at here? This big, big blob of color. Mm-hmm. Green is quite dominant. What does green look like? Says no thermal stress. I don't know if you can see that on Zoom. Hopefully you can. As we go orange, dark orange, red, kind of really deep red, these things are labeled moderate heat stress, strong heat stress, very strong heat stress, and extreme heat stress. What?
Related to human comfort.
Exactly. It's using this thing called UTCI, which is the Universal Thermal Climate Index. And what it says is, if you are an average human and you're outside with no shelter in this location, for every hour of the year, it's going to give you a score for like how much stress your body is under in order to stay alive. So all the bits that are blue is basically saying you are going to be struggling because it's going to be too cold for you outside. All the bits that are green, no thermal stress. Actually, you know what? Pretty happy to be outside. I just wear some normal clothes. No one's going to I'm not thinking I've got to get inside right now. Anything that's kind of orange and yellow, you're thinking I am way too hot. I need to get in some shade. I need to get into an air-conditioned room. I need to get out of the sun. So what this kind of gives you roughly is an idea of like, if you live in London and it's 4:30 in the morning on February the 1st, can you all see that? This is an average year at 4:30 in the morning on February the 1st, it's minus 17-ish degrees C and it's strong cold stress. So if you're homeless in London in February, it's bad news. Now, obviously, if we change this to like Moscow or something, there'll be a lot more blue. You get the idea that you can go back and forth, you can change locations, you can do all sorts of different things. But this gives you, at a glance, this is your year divided into hours of the day when you know what the human body is going to be experiencing if it's outside in your location. I mean, you can change this, but the UTCI is an incredibly good metric because it gives you a human feeling. And that's what we want to get to. Like, we don't care about numbers if they don't mean anything to people. What we do care about is, I would feel really cold or I would feel really hot. UTCI is really, really helpful for that. Okay. There you go. Those are our site analysis tools. We've got
What's the wind protected shaded boxes. Does that do anything?
Okay, well, here we go. If you click shaded, what's going to happen is it's not just going to say you're outside with no shelter. It's going to say you're outside, but you've managed to get under a tree or under a building or something and you're in the shade. So let's see what happens. What happens there? Right, so there's a little red bit here, which says moderate heat stress. Yeah, when we go shaded, the red goes away. So that's good, except all the green bits are now colder. Yeah, so you're saying, okay, great to be in the shade. But if you're in the shade in March, you'd actually rather be out in the sun. Like today, if you're outside and you're wearing a coat and you're in the sun, you might feel it okay. But if you're outside and you're in the shade of a big building, the wind is kind of whipping past you and it's not very pleasant. And this exactly, like you can start playing with these things and get a really good intuitive understanding about what the weather is really like. Wind protected is very similar. So wind protected is probably going to affect not just if I'm out and about, but I've got some kind of shade, like wind shield. And what's going to happen here is our extreme cold is gone, which is good. But we've actually now got more extreme or moderate heat stress because that was giving us a breeze at that point in the year. So do you see how that works? Start playing with that. I mean, that to me, that's an interesting portfolio page, isn't it? To understand what aspects are going to make a big difference, not just on the one day where it's really hot, but like across the whole year. What's interesting about this climate in this country is that people spend a lot of time thinking about, oh, I've got to put brise soleil on my windows, on my south-facing windows. I've got to shade my south-facing windows because otherwise it will be really hot in the summer. Except what this is showing us is by shading your south-facing windows, what other thing are you going to end up doing? It's going to get more cold inside your building at other points in the year. And for the sake of the 1 or 2 days where it's really worth having, you might end up paying more on your heating bills for those other parts of the year, which is exactly why what you'd really like is some way of shading your building in the summer, but not shading it in the winter. And there are two obvious ways that people end up thinking about that. When I say, oh, wouldn't it be great if we could have a way of shading the building in the summer, but not in the winter? Most people jump to, oh, well, I'm going to invent some crazy fancy system which of like opening and closing louvers and like some kind of mechanical thing. And the other people go, I'll plant some trees. Yeah, okay. Anyway, that you can use this as argument for why I'm going to plant this plant outside my building because it gives me leaves in the summer when I need them. And you could then match the season when the leaves are in with exactly when you want more shading, whatever it is. It's your project. I'm not doing it, but I find this stuff exciting because it gives you design ideas that are real. Yeah. Okay. Site analysis. Tick. Should we have a 5-minute break? I've waffled, but there you go. Pause my sharing. How's everyone online? Have you been following along? Everyone happy?
Happy. Yeah. Very useful.
Good stuff. We're going to take 5 minutes. We'll be back at 10:05.
Okay, great. Thanks. Thank you.
I listened to Christmas.
She's ready to sing.
You know, all the classics. Driving Home for Christmas by Chris Rea. Good song.
Right. We've done site analysis. Next, point in time illuminance. Point in time illuminance. We are recording this, so that's good. In order to do an illuminance study, actually what I'm going to do is dock this back where it was before, because I want to be able to see my model here. Let's just turn the windrows off. There we go. And I'll take the shadows off as well. Here we go. So point in time illuminance is another workflow. So ClimateStudio has these workflows. We've done the site analysis one, and we're going to work our way through the point in time illuminance. What that means is you choose a specific day and a specific time, and it tells you how much light is going to hit the inside of your building, which seems pretty simple, but it's putting numbers on the thing that you can do in Rhino, where you just do a little render with the sun turned on, or you do a screenshot with the sun turned on. That's gonna show you where the sun is hitting and where it's not. But this is going to show you actually how much light you get in numbers. And you can then start to make sense of some of those numbers. We'll have a look at that. So we need to tell it some things. One of the things that we need to tell ClimateStudio is what the sky is like. Is it overcast? Is it clear? What's happening? I'm going to choose a clear sky, and I'm going to set the dates. I don't know. Let's choose. Should we choose a solstice? Is it June 21st? Is that right? June 21st at midday. Something like this. Here we go. So I've set up a clear sky on June the 21st at midday. And we can visualize, if we go back to the site analysis, we can visualize this June 21st at midday. We can literally say, well, we know which way the sun's going to be coming because we can see it in the 3D sun rows or sun path, can't we? So we can see it coming in this direction. Actually, midday is kind of an annoying, like a boring time. Let's try like 9 in the morning. Let's do 9 in the morning, because then you get this nice angle and you can see a few different things going on. So we go back to point in time and illuminance. You see these times, they change independently. You can have your sun path at one time and your point in time illuminance at another. 09. There we go. It's 9 o'clock in the morning, and we need to tell ClimateStudio what different materials the main parts of our building are made out of. The reason we need to tell ClimateStudio about these materials is there are some types of materials that are going to let light through, like glass, and different types of glass are going to let different amounts of light through. And there are some materials that are going to let no light through at all. So from a daylight point of view, the wall, for example, our wall here, when we assign materials, it gives me a list of layers that I can see in my model. And there's wall there, and it says material none. See that? I'm going to start off by saying, click on the none, and it gives me this thing that lets me select a material. There's loads of materials here. The main thing to be aware of is there are 2 types of materials in this drop down just here. One is called a glazing assembly, and these are different types of glass for which ClimateStudio has data. So you can choose any kind of glass that's kind of imaginable by man. Triple glazed, double glazed, tinted, not tinted, completely clear. Yeah. Other is everything else that isn't glass. So is it what? Brick? Is it timber? The thing is, for a daylight study, no one cares. If it doesn't let the light in, it doesn't let the light in. So I'm just going to say, I don't know. It's a very boring building. It's a brick building. There you go. Select that. The roof, again, you know, maybe if I want to be really like a dark gray aluminium roof, okay, fine. But no one cares exactly what the roof is made out of for a daylight study, as long as it doesn't let the light through. And aluminium doesn't let light through, so they'll give us shade on the roof. The floor, I don't know, like a beige floor tile. I'm being really boring here. You have to say something, because otherwise ClimateStudio doesn't know what to do with this. So I'm just going through the visible elements of my model, and I'm telling ClimateStudio whether this thing is going to let light through, and if so, how much, or whether it's not going to let any light in at all. Glazing, I'm going to choose glazing assembly. Yep. The zoom's gone. Oh, no. As in the screen share.
I can still see.
Oh, okay.
Yeah, me too.
Oh, everyone's fine. Okay, good. I'm glad to hear it. We're applying a glazing material to our glass. And what you'll see is when you change this drop down to glazing assembly, you've got loads to choose from. But what we're going to look at are some of these values. Who's familiar with the idea of a U value? Who's come across a U value before? Can anyone explain what a U value is? Putting some people on the spot.
Energy coefficient or something.
An energy coefficient, something to do with insulation. How much heat?
It's the amount of heat that goes through all the layers of the wall, floor, whatever.
So it's the amount of heat energy that will be let through a particular sort of square meter of a surface in watts. So, and it's measured in watts per meter squared Kelvin. So what you have to imagine is you've got a surface. It's maybe glass, maybe it's a wall, maybe it's a roof, maybe it's a floor. It doesn't matter. It's a surface. On one side, you've got an environment that is 1 degree hotter than the other side. Yeah. If it's 1 degree hotter, then that heat wants to go through the wall to the cold side. It wants to average itself out so that it's all kind of the same. What the U value tells you is how much of that energy is going to get transmitted from one side to the other. So a really, really low U value is, well, depending on what you want, rather than thinking about it as good or bad, if it's a low U value, it means more heat energy is going to stay where it's supposed to be or where it was. Depending on which climate you're in, you may or may not want that. Does that make sense? And this is why the site analysis is really important, because actually, if I don't know, if you want the same temperature inside as outside, you want a high U value. You want things to be able to pass through easily. Okay, so what you could do is you could look through glass, all the glass information, and order it by U value and pick a U value that you think makes sense. I don't know, maybe we could find one that's like 1.2. Here we go. Look at that. We've got an option there called OptiGray Solar Band 70. Now, I don't pretend to know exactly what these products are. You can Google them to your heart's content. Personally, I don't really care what the make and model of your glazing is going to be. What I care is that you have some understanding of how that's going to perform. But let's have a look at some of the other information here. TVIS and RVIS. What do you think they might be? TVIS and RVIS.
Was there R value as well as a U value?
Is that R value and a T value? An RVIS.
Thermal resistance.
It's not going to be thermal resistance. The U value is effectively thermal resistance. The vis is a clue, visible. Visible or visibility or visible. Yeah, visible. It's a measure. Transmittance, lovely. What a great word, transmittance. And then R is reflectance. So let's find a picture of some mirror sunglasses, right? Okay, look at that. What's the reflectance value? Is it high or low for these sunglasses? High. If it reflects a lot of light, Does much get in? No. So with sunglasses, you want to shade the amount of light coming into your eyes. So you make them shiny, so they reflect, and then you make them not transmit as much. On the other hand, oh, can't. Right, these glasses. What's the reflectance on those? Very low. Wants to let the light in. What's the transmittance? Transmittance, high, low. It lets the light through. It transmits the light through. So it's going to be really high. Okay. So what we're talking about is the difference between our mirrored sunglasses kind of glass and our really, really clear transmitting glass. And we can look at those here. So this one that we just selected, which has a U value of 1.2, so it's, you know, it's not great, it's not bad, it's just a fairly standard double glazed unit. It's got a little diagram here. It's got glazing and then some noble gas on the inside, and then another type of glazing. But it only transmits 45%, or it transmits 45% of the light that hits it, and it reflects 8.5% of the light that hits it. Whereas something like this one, to compare, this one is called clear. What's the difference between optigray and clear? Well, clear has a transmittance that's higher than the other one. So this one is going to let more light through. So what we can do is we can start to play with some of these. Let's just choose one that's clear for now. And I'll select that. So this is clear glass, is going to transmit lots of light in, and the U value is kind of, it works thermally. But we're doing a daylighting study, so we don't really care so much about the U value. We care about transmittance and reflectance. So how much of the light hits it is going to come through into my building. The mullion, I mean, it's just going to be aluminium or something, isn't it? Choose a metal. There we go. The roof light, aluminium metal cladding, fine, okay. And then the glazing is going to be similar, glazing assembly, and it was called clear. It's one of these, wasn't it? 63%. Yeah. There we go. Okay, so now we've put the same glass in the roof light as we have in the windows. Next question, it asks us to add luminaires, as in like artificial light sources within the building. We're not going to care too much about that. We just want to care about daylight. So the daylight that comes through the windows. That's the thing we've got control over, really. Then the last thing it asks us to add before we can actually run the simulation is add areas. And those are the areas where you're actually going to be measuring how much light hits. Because at the moment, ClimateStudio doesn't know where's the inside of a building, where's the outside of a building. You've told it nothing yet about where to measure. So you click add areas, and there's a little button there that has a plus next to a little square. And add an occupied floor area, and we're going to select surfaces or meshes representing regularly occupied floor areas. Well, luckily I've set up a floor. Here it is. There it is. There's our floor. Press enter when done. Here we go. And it gives us a few different options. I'm going to give it an ID of my room 1, because you might have separate rooms. So you have different areas for different things. The sensor spacing is 600-ish millimeters apart from each of the sensors. So each of these dots is now going to be sensing how much light hits it on the 21st of June at 9 a.m. And then it offset is 762. So what it's done is it's taken the floor, but then moved it up 762 millimeters. So put our sensors in a bit more of a sensible kind of desk height kind of thing. Rather than measuring it on the floor, we're measuring it at a working height on a desk. And you can change those values if you want, but we'll just go with the obvious ones. We're not going to add any tubular daylighting devices. So you could design something where you have a kind of a light trap, which is kind of like a big periscope that brings the light in through your ceiling, which is like a tube and that bounces around and gives you this lovely diffuse light. if you want, you can add those in. But basically, we're now set up and we can press this little guy here, the play button, and we can see what happens. Let's just zoom out so we can see the sun's coming in this angle. You press play and it will do two things. It will bring up a results file, results window, which I'm just going to dock there. So we can see the results. And it'll do a whole load of these passes. So what it's effectively doing is kind of like a render, but it's using that information about the glazing that we've provided and about all the shadows that are going to be made. And it's doing it again and again and again and again, and giving us exact lux levels for what's going to be going on in this building at that point in time. That makes sense? So now you've got this heat map where it's red. You can see the lux levels are pretty high, 34,864 lux. And I would Google how much is a lux, but that's a lot of light coming in.
Check the similar feedbacks, and it suggests to you where you should place your internal lighting.
Yeah, so, well, this isn't going to tell you where you should do things, but you can then use this map to say, well, in July, these lights are going to be on, and these lights are going to be on, and these lights are going to be on, but here, no one needs any light. Yeah. It also gives you a rough idea of like what the mean amount of light hitting the inside of your building is on that day and at that time. And it shows you this in a way that is fairly obvious. You can see the light coming through at this angle from the sun path. So you know you're going to get this shadow from the roof lights. You're going to get this area of the light coming in through this south-facing window, and you're going to get this area of light coming in from the east-facing one, or west-facing one. Oh, east. There we go. Okay, great. We've got some numbers now for light. So there's a few different things we can do. What we can do is go back and change our material to a more reflective glass and see how that affects the numbers. So you could do that. I'm not going to do that because it takes a little bit of time and I do want to move on and get us to looking at other things. But do you see how you could now use this to do a qualitative analysis on different days of the year to really show how much light's coming into your building? Okay, great. There's something better we could do. Imagine with me that you are a very, well-paid architecture firm, and you have the joy of having an unpaid intern at your disposal. They will do anything for no money at all, just for the exposure. And you say to them, hey, listen, we've got this problem. I could sit here and do this, take all these numbers, and then change this to 10 o'clock, and then do the run again, and then wait for it to do 100 passes, and then look at all the numbers and then capture that data, and then do this for 11 o'clock and 12 o'clock, and every hour for the whole year, and average all of the numbers together. I could get my unpaid intern to do that, and it would take them a very long time. And what you're effectively doing is asking a computer to send a little unpaid intern to stand in each one of these positions at a certain point in time of the year and write down how much light's hitting their face effectively. But no one has time for that, not even an unpaid intern. So this gives you the next thing down, next workflow down is something called daylight availability. And what this is going to do is calculate something called a daylight factor. And the daylight factor is going to be not just one point in time, but an average across the whole year for how much daylight is going to hit that one particular place in your building. So we've already set up materials. We've already set up areas. Everything's set up for us to do this. We're going to run a daylight factor analysis using daylight availability. When we do that, we start to get a very different pattern. Do you see how much this is kind of blurred out compared to the previous one? That all of this is averaging out to say, effectively, the sun's coming round, look at this hour, this hour, this hour, this hour, this hour. Next day, look at this hour, this hour, this hour, 365 days of the year, using the information that we have in the Energy Plus weather file. So it's taking into account how many days are overcast in the year, where's the sun coming from each hour, adding it all up and giving us what they call a mean daylight factor. And what daylight factor is I like to think about it like this. When you go to the cinema, who's been to the cinema in the middle of the day and then come out of the film into like sunlight? What happens to your eyes? It takes like they hurt, you know, because you've been in this really dark room and then you come outside and it's like, oh, the sunlight hits you. That is a really low daylight factor, because what you're effectively saying is the outside sunlight is at 100%. And what I'm experiencing is a very, 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 very tiny percentage of that outside light coming in. In a cinema, it's zero, isn't it? Because it's completely enclosed, dark room. And maybe you get some light from the screen, but basically, when you walk outside, it's like it hits you. It's huge. However, you could be in a place where there's lots of glass and almost all the light from outside is coming inside, like a greenhouse, for example. And then when you walk outside, it's like nothing's changed. So a greenhouse with completely clear glass that doesn't reflect any light at all would have a daylight factor of 100% if it was made purely of glass. What this is saying is that we've got a daylight factor of about 6.5, 7%. And what you could then do is like do a bit of Googling and read about what daylight factors are good for different things. If you've got a daylight factor of less than about 2%, it's going to feel a bit dingy inside your building. If you've got a daylight factor of more than 5, it could be really good for like for an activity that needs lots of light, like, I don't know, watchmaking, where you need to like have lots of light on a very small piece of equipment or something. But you might have some trouble with just having too much light. Like right now, this sunlight is in my face and it's kind of annoying. So maybe I praise myself for having a high daylight factor, but I also have sun in my face for half the year and it's annoying. So you've got to kind of weigh these things up, like what daylight factor is going to feel good for what you want to have be doing in your building. And again, we can play with it. So we can change the materials, or look, we can change the roof from roof type 1 to roof type 2. And we've now got some shading over this big south facing thing. And let's run our simulation again, remembering that roof 2 doesn't have a material yet. So now I've got to add a material to roof 2 because I turned roof 1 off, I've turned roof 2 on. I'm going to give it a material, search for roof, dark gray, aluminium, fine, whatever. And let's run. Okay. Doing a few passes. Already you can start to see that that's made a difference to this area here in terms of how much daylight is hitting that area of the floor of our building. It hasn't made much difference to this area because there's still a great big honking roof light in the ceiling. And you could see, you can then go away and play and like, well, change that roof light out for roof light 2, add materials to that one, see how much difference that makes where you have a north light rather than a flat one. Once that's finished, you can now see daylight 1 had a 6.9% mean daylight factor. Daylight 2 had 5.8%. So by bringing that shading out over the south wall, we've brought our daylight factor down by 1%. And what I want you to do is not get hung up on the numbers, but focus on the fact that this is now a tool for you to start pulling your building around to get the outcome that is going to feel good for the people inside. Yeah, because we're designing for humans. We're not designing for spreadsheets. Great. Okay. Are we happy with daylight factors? Make some sense? Great. And if you're into like Design Builder, you can do much more. And I'm sure there's much more you can even do with this. For you, it'd be really interesting as also, I'm sure, to think about different areas in your building and how much light they get. But anyway, there you go. So we can start pulling things around. Okay, that's daylight availability. Let's look at glare. So glare is the flip side of having lots of lovely natural light into your building. In a moment, we'll also have time, hopefully, to look at the thermal side of things. Daylight availability, glare, and thermal solar gain are three sides of a coin that will never quite match up the way you want them to. Because if you think about it in terms of, but I lose heat through my windows, you'll end up designing something with very small windows and your daylight factor goes to dingy, dingy, horrible place. If you think, oh no, but I don't want people to have sun in their eyes for any of the year, you'll end up shading all of your windows and spending more money on heating. If you maximize your daylight factor to get lots of lovely natural light into your building, but you then also say that you want people to learn in your building, then both the glare and the heat are going to be potentially a problem. Does that make sense? Like, you've got these things to play with, but none of this software is going to give you the answer. You have to work out what you're willing to live with and what compromises you need to make somewhere that is going to be nice and is going to actually match the human aspects of your design, but and not become, what's that? Have you read about the new student halls in America?
Yeah.
1.5 billion and no natural light. Like, in some ways, there's an argument to say that that is like a surprisingly sustainable way of doing things, because by having no windows, it makes it cheaper to heat and you can fit more people in and it's more efficient. But how do you think it's going to feel living in a prison with no natural light? Like, sustainability from metrics versus sustainability from you as a designer and wanting to create good spaces for people need to be brought into line. And so that's why we're giving you these tools to be able to have those conversations. I won't go on about that because we're running out of time. But do you see now that I'm pretty sure you can guess what I'm going to do. I've just switched my thing to annual glare. I've already set up my materials. I've already set up my areas. Everything's good for me to go. I'm going to hit go. By the way, every time you run a simulation, the results are saved. So now you can go back, you can look at any of the results that you've got before and you can compare them. So just because you've run one and then you run another one, it won't have lost your previous results. That's why it brings up this CS results window, which is really helpful because then you can, again, a portfolio page, a beautiful portfolio page of like, this is the difference between shading versus not shading that window in terms of the daylight factor. Here's a glare analysis. So what this does is it takes our unpaid intern and has him sit in every single position of the room for every hour of the day, for every day of the year, and face in 8 different directions and asks the question, is the sun shining in your face and is it annoying? Is this annoying? Is this annoying? Is this annoying? Is this annoying? For the whole year, every hour, in every single one of these locations. Like, this is why computers are great. Yeah. And you can see a lot of red here. Like, if you're sitting here, unless you're facing directly away from the window, most of the directions that you could look, the glare is going to be in your face.
Wouldn't material make a difference in glare study? Because if you have something that's reflected on the inside of your building.
Exactly. So that's why the glazing has 2 reflective values. One is RViz front and one is RViz back. What that says is, if you shine a light or some sunlight's coming in from the inside of your building and hits the window, how much of it gets reflected back into your face? So that takes that into account. But to combat, one of the things you could do to combat glare is to go to your glazing material here and choose one that has a lower transmittance and a higher reflectance. So it limits the amount of light coming in to your building in the first place. And that's going to mean that these red Pac-Mans are going to reduce, because there are more situations in which you can say, this glare is okay. There's quite a nice thing called radiance rendering, which you set the sun on a particular day. So this isn't throughout the whole year. And you set the materials, and then you say, click render window. And what it will do, you have to pick a location, and you also have to set a height. So I'll set a height 700 millimeters above the center of roughly the center of the model. There we go. And I'm going to click start. And what this does is like a really rough render, but it does it in a kind of fisheye lens thing. And it's set, because I know the date, I've set the date to be, what is it? At 10 o'clock on June the 21st. And I've said that I'm standing right in the middle of my building, and then I can drag this to look around in different locations. And if I drag it, at each point, it'll tell me what the level of glare is. You know, how would I feel if I was standing there looking in this direction? Would my eyes be hurting me? And as I move around, potentially, maybe if I choose a different time, we'd see it a little bit better. Here we go. Let's choose 8 o'clock in the morning. Stop that render, and I'll change that to this. Start. There we go. So the sun's coming in from a much shallower angle. You can see the light from the roof light is now on here. But if I turn my render window around, I'm basically one of those little Pac-Man things, and I'm turning myself around at a specific point. But now, when I look through this window, I suddenly get perceptible glare. It's orange. And if I went and stood in that like sunlight, it would change to red and be like really unhelpful glare. So again, this could be, I mean, I don't think this is a particularly compelling image, but it's helpful to understand what's going on in the computer when it's running these simulations. Does that make sense? Cool. Good. Okay, so there's your glare. And again, you know, this is a design tool. So you tweak your design, you make changes. And what I would suggest you do is don't let your design be driven by this. Use this to test out different options, and then go in the direction that is going to give you, you know, like if you sacrifice all aesthetic for the numbers, what are you as a designer? Like, have a vision and go for it. Right. Very quickly, in the last 10 minutes, let's talk about thermal analysis. And thermal analysis involves taking this daylight model, just turning the whole thing off. And instead, what I've got here, I wonder if I can get rid of these results. How do I get rid of these results? Oh, well, so it looks like I can't. By the way, if you need to get the results back, it's this little graph up here. So you hit results. And I wonder if there must be a way of like hiding it, because it's kind of getting annoying. But anyway, don't want to delete. Oh, well, doesn't matter. It's fine. We can carry on. Thermal model is this. And it's super, super simple. My building was a box. This is a box. I got my box tool and I made a box. It's a closed volume in Rhino. So all of the edges are exactly linked together, and they're all joined up, and it's got a roof and some walls and a floor. That's it. And it's paper thin, like infinitely thin. You don't have to worry about thickness. It's just a box. And inside the box are some people, and outside the box, there's the outside.
Quick one.
Yeah.
If you have some organic shapes,
Yep.
in order to get the terminal study, and you just build volumetric boxes that almost like mimics your structure.
Yep.
So that you can assume.
Well, if you, let's say you've got an organic plan like that, yeah?
Yeah.
And you've extruded it. Extrude, curve. Then you get, if I switch to ghosted, you'll see, you get this, right? But it needs to be closed. It needs to have a roof and a floor, so I can type cap. And that gives me a closed poly surface. One closed poly surface added to selection. You can check by clicking it, and it'll tell you if it's a closed poly surface, open poly surface, 3 poly surfaces, in which case something's wrong. It needs to be one closed poly surface. Now, there's other ways you can do that. You could start with, if you've got a really organic shape, you could start with, for example, a sphere. Yeah. But then Control Shift and like pick some of these guys up, or points on, and then start to kind of pull these around. Yeah. Either way, that's still a closed poly surface. So when you click on it, it's a one closed surface. Even better than a poly surface, it's one surface. But most of you are going to find that you don't have to model this to the millimeter to your building. Think about it in terms of, if you pretty much get there, then it's good enough for your thermal model. Yeah, that makes sense. So you're making a thermal model, but it's going to take you literally 5 seconds to do, as long as it's closed. Okay, and what this is going to say is add objects. It's italic because it doesn't know any objects yet. So we need to tell it about some of the things in our thermal model, because a thermal model is different to a daylighting model. So we're going to add some objects, and the first thing is zone from template. I'll click zone from template, and it'll say select closed volumes as zone geometry. What we're saying is this is a closed zone where inside is an atmosphere and outside is a different atmosphere. Yeah. And in fact, actually, what we're going to say is outside, just the climate, and inside is what I want to keep at a nice, comfortable temperature. And then we'll give it some other information as well. Press enter when done. There we go. If you've got multiple rooms and they are thermally separated, so there's a wall with a door that closes, and that wall, you expect there to be a different heat on one side than the other. So you could have a greenhouse and then a door that closes and then you're inside, or sauna and then a kind of somewhere in between and then the outside. So you're going to have multiple zones that you model as closed boxes. Okay.
Can model them separately then.
Yeah.
Like,
absolutely, yeah. But
not
they
within that one building.
well, so you could model it as one whole thing with a divider. I think I'd have a go and play with it and see where you get to. Or you could model them as 2 touching volumes that share a wall. And then once you've selected it, it's going to ask you what you're doing inside your building. And that's useful information because it's going to use that to say, well, how does this need to be really warm in here? Does this need to be really cool in here? Is it going to be used all the time, or is it going to be empty some of the time? And if it's going to be empty some of the time, then maybe I don't need to heat it during the night or whatever it might be. If I say it's residential, then it's going to try and aim for, I think it's something like a 20 degrees C average temperature all the way across the year. So it's just going to say there's always someone here, probably during the day and during the night, and I want it to be this nice livable temperature. So I'll just click select residential. You can play around with the different options here. Maybe office is going to give you some different values because people don't tend to work in the office at 2 o'clock in the morning. And then we've made a zone. Great, we've made a zone. And it's got some really nice things going on. The first thing that is done is it's actually, I think it's already, I had already been playing with this. I'm just going to delete these windows because usually you have to add the windows yourself. I think when I was playing with this before, it's remembered that I put the windows in. So sorry about that. Here we go. We've got a facade, a facade, a facade, a facade, a floor, and a roof. So we've got 4 walls, a roof, and a floor. Really easy. And what it's done is it's giving these some information. This has a U value of 0.2. Just it's randomly chosen some value of 0.2. What we can do is we can edit this zone and change the envelope. So we can say what the actual U value of the wall is going to be. So if you choose facade, there'll be a whole load of build-ups here that you could choose from. Let's say, what we got? 120 mil insulation and then some solid wood. Maybe this is a good place to start. It's insulation and wood. So it's a timber insulated building. And then there's some like plasterboard on the inside and maybe some render or something on the outside. Who knows? But once you've selected those things, then it's going to update the facade with that information. So you say, this is what my building is made out of. This is how it's going to perform. The floor, similarly, I click edit in my zone and I can set the floor. Maybe I'm going to choose a roof that's, I don't know, 160 insulation and 94 solid wood. You can play around. You can choose these values to your heart's content and see what difference it makes. Again, it's not about the numbers. It's about understanding how they change things. I'm just going to leave those for the sake of this demonstration. I'm just going to leave those for now. And then the next one along, you basically just move from left to right. So it says add edit window. We're going to select this window geometry. One of the things you'll notice is this is kind of like flickering. What that tells you is that these two surfaces are like right in one another. They're infinitely thin, but they're like exactly in line. And it needs to have the windows as a surface that's exactly on that facade in order to work. Otherwise, it'll get really confused. So I go round and I select my windows. Boom, 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 boom. And there's a big one down here as well. There we go. And we can set the glazing. Glazing is going to be whatever we want our glazing to be. I'll just choose one randomly for the sake of time. We can tell it that there's some exterior shading, but I'm going to leave that for now. I've made this shading here, but I'm going to leave it off the simulation for now. And there we go. Then next one along, internal windows. So you can have internal dividers which have windows in them. And it'll model that. That's kind of cool. You can add edit shading. So that would be really simple. You just click it and then you choose that shading and say it's shading. You do need to add the ground though, unless your building is like Lisa's, like floating above the ground, it's going to have a connection to the ground through which heat doesn't really flow because the ground is a much more stable temperature than outside. So the boundary surfaces, I've modeled this as a flat surface on which this is sitting. And again, it's flickering because the ground is like literally through the floor. Enter when done. There we go. And it's made a ground boundary. Now, we're pretty much ready to go. The adiabatic boundary is already set because I've told it what the ground is. And all I need to do is press play. It'll do this hacker code thing, which is very exciting. And that'll give you a nice graph. And you go, great, I've got a graph. What does this mean? I've got 5 minutes to explain to you what the graph means, and then we'll maybe try and play around with it and see what happens. The graph, it doesn't display anything in the viewport. So it doesn't give you this lovely heat map of like, oh, there's a hot bit of my building and a cold bit of my building. It just says, no, the air in your building is all one thing. But what we care about is at different times in the year, we're going to need to do different things to make it comfortable to be in. So what you have to imagine is a man lives here all year round, and the man has his thermostat set at 20 degrees. Or oh, look at this. No, even better. The man has his thermostat set at 19 degrees. His thermostat's at 19, morning, noon, night. That's what's happening. Always 19 degrees. It's the easiest way of doing the maths. And don't worry too much about getting more complicated than that, just because this is a comparison thing rather than anything else. Yeah. Yeah, exactly. Especially if you've got half inside outside spaces, they're going to share the climate with the outdoors. Even though they're covered, they are going to be shaded in the summer, open to the wind in the winter. They're, you know, don't, if you've got 2 rooms inside, probably, and I don't know, but probably you could model them as a single volume, because if you walk into your house and you've got your lounge and your kitchen next to each other, you can leave the door open, and it doesn't really matter which room you're in, the temperature is kind of the same. So probably you're going to end up modeling things as a single volume, like I've got here, which is why I'm showing you this as a kind of simple start. Your simple volume is actually going to be probably quite similar to this when you actually start breaking down your building. Even if you have an organic shape, you could probably model it as a box. I'd be really surprised if you couldn't. That makes sense. So yeah, when like I wouldn't expect you to go into more detail than what I'm showing you here, but it would be really good for you to have a go at this and then apply it to your building and say, oh, how much difference is there between this box and my building? Actually, not much at all. Well, I'll just go with the box then. Yeah. So here we are. We've got this box with these openings and this glazing of this material, whatever it's going to be. And what this graph shows us is in January, February, March, blah, 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 blah. In all of these times of the year, how much energy do I need to keep the inside of my box at that perfect 19 degrees Celsius? That makes sense? So like, if you imagine in January, what do you think the weather's going to be like outside in London? Cold. So what do you think this big red thing is going to be?
Yeah, heating.
Right. So we're spending energy on heating our building to keep it warm because it's cold outside. And if we're not careful, if we don't put the heating on, however good your U values are, it's going to get cold in there. It's just a question of time. So and then there's a little key down here. In fact, if I make this bigger, you probably see it. Key down here, the red is heat. It's got a yellow thing for light. I mean, I'm not sure how accurate and how great that is, but fine. The main thing is the heat and the cool. So what this is telling us is in January, February, March, and then our heating bills are going to start coming down. Are we all pretty happy with why that might be? Yeah, the amount of energy that we need in order to keep our building at this lovely 19 degrees. Well, until in July, what's great is that the average temperature in July in Oxfordshire is around about 19, 20 degrees. So you're not going to have to spend lots of energy to heat your building, maybe in the middle of the night, but not much other than that. And then obviously as the year goes on, it costs you a bit more, it costs you a bit more. But then you could then go back to change your materials, add more insulation, add more glazing, change how big the windows are, change how much shading there is going on, and see how it affects your heating costs. So here's an interesting one. Let's go and add that big shade over the window here. In fact, I'll make it nice and big so you can see. At the moment, we haven't modeled it at all, but I'm going to go this, add edit shading, and it's added a shading object, which is the one that I just selected. I already had it selected. I just clicked add shading, and there it is. So now it's a static shading surface that's there all the year round. And what do you think is going to happen to this graph when I run this simulation again? Any guesses? What's that? Yeah, I've added shading to my south-facing window. I'm going to need to heat it more. Was there a problem with it being too hot and needing to be cooled down? No. Okay. And in fact, actually, if I changed my insulation to a much thinner one, for example, I might end up with a problem of it overheating. And then I might need to add shading. But anyway, let's do it. We've added the shading option. I'm going to run the simulation one more time. And here's energy 1. Here's energy 2. Energy 1, so that was without shading. And I can give it a little no shading, give it a little name. Energy 2, shading. And in fact, even better, I can select both of them, hold down Shift and select both of them. And there's a little button that says compare. And this brings me up a comparison window. No shading
2% more.
uses 2% more energy. Is that what you expected? Is that helpful information? When someone looks at your design and says, why haven't you put a brise soleil on your window? Have you got an answer? There you go. This is why this stuff can be really, really helpful. And it can release you from some intuitions that you may have thought were wrong. Now, if we changed our location from London to Abu Dhabi, let's do it. I'm pretty sure that shading is going to make a big difference, isn't it? Yeah. And I'm pretty sure what it's going to make a difference of is we're going to have almost no red in our graph, but we're going to have a whole load of blue for cooling. Okay, let's come back. Up. Abu Dhabi. Download that. Haven't done this before, so we'll see what happens. We set everything up. Here's our zones. I'm going to get rid of shading. So there's no shading now. I'll run the simulation. Here we are. Boom. We've changed our location. We completely changed our energy profile. That's no shading at all. I'm going to, oh no, that's an internal window. I don't want that. Add, edit shading. Here's some shading. Enter when done. There it is. Run the simulation again. Boom. Now I've got this one, Abu Dhabi, no shade. This one, Abu Dhabi, shade. Select those two, compare. No shading uses 5% more energy. Have we got now some tools to start playing and making some bold moves with our designs and not get bogged down by the numbers, but just think about them in terms of, are we moving in this direction or are we moving in this direction? Do we care about glare? Do we care about daylight factor? Do we care about thermal performance? Do we care about daylight availability? Do we care about view angles? How does that impact maybe even, this is a cool thing, you can grab your whole building and rotate the whole thing and rerun your simulation and get a different result. Yeah. Okay, I'm going to leave it there. That's ClimateStudio. All the information is in the file. You should be able to just install it as you go. And hopefully within the next couple of weeks, we'll have it on all of these computers here as well. but help each other out. So if you've got Rhino on your laptop and you've got ClimateStudio running, buddy up with some other people and say, can I run some simulations with my model? Because it doesn't take long. Like we did that whole thing in 2 hours. So if you get together on a non-studio day, I'm sure you can basically churn all this stuff out pretty simply. And suddenly there's a compelling design argument for your choices. Okay. Any questions, or should we move on with the day?
Once you install it on any of these computers, is it going to be there, or do you have to install it every time?
No, it should be there. Literally, the idea is I'm going to work with Marcello to make sure it's there, that every time you open it up, you see these options. Sorry, say again? Oh, no, sorry. Okay. All right, good.
Thanks, that's really.
All right, useful?
Yeah.
Good. Well, I mean, shout on the WhatsApp as well between you. If one of you can't work it out, then fire off a question. If it's about installing, I probably won't be able to help because all I know is that I double clicked the installer and it worked. So other than that, you're kind of on your own. I'm going to stop recording now and I'll put this up online for you to look back over.